Sure, my name is Nikita. I am from ECE branch. My subject is microwave and radar engineering, and my topic is real time generator for noise radar. Coming to introduction, noise radar is a form of random signal radar that employs a noise waveform as a transmitted signal and uses coherent processing of radar returns. It has been known for many years and has both civilian and military applications. Because of the truly random transmitting signal, noise radars have many advantages compared with conventional radars, including high interface immunity and high electromagnetic compatibility, very low portability of intercept, and good electronic counters. Countermeasure capability. These properties increases the noise radar importance in military applications, and it also known from the many years, and it can be used by the both civilians and military applications. In this article, our main motivation is to generate pseudo-random samples with different distributions and to create a testing environment for the target decision performance. For this purpose, we develop a real-time digital signal generator on an FPGA by adapting and improving our previous effective pseudo-random number generator for noise radar, and it used some different distributions to create an environment for a specific performance. The article is organized as follow. In the second section, we prevent background information on noise generation method and algorithm on FPGA. Details of FPGA implementation of noise generation methods are described next with the numerical result. And the final session presents a summary of the work and suggests topic for the future resources. Noise generation method. One of the most common implementation for the pseudo random generation is using linear feedback shift register, that is LFSR. It consists of a shift register where the bits at several positions are combined with exclusive or NOR operation and fed into the least combined with exclusive or NOR with the registers on each clock cycle. A maximal length, that is LFSR, can generate uniform random variables with a periodicity of 2 power n plus 1, where n is the number of orders of polynomial. An example includes x power 4 plus x cube plus 1 polynomial using the LFSR. Here is a diagram which uses some shift register, and the output of the first register is connected to the input of the next register, and the input and output connected between the XOR gate. Using both leap forward LFSR and Thusworthy generator, uniformly distributed pseudo-random samples whose PDF is given. They are generated by f of x is equals to 1 by b minus c. For a less than or equal to x less than or equal to b, 0 for 0. And the Box-Molechner algorithm can be represented by the following two equations. X0 is equals to under root minus 2 log u0 into cos of 2 pi u1, and the x1 is equals to under root minus 2 into log of u0 into sine of 2 pi u1, which combines the given equation is f of x is equals to 1 by 2 pi size rho square into e power minus x minus rho square by 2 rho whole square for minus infinity less than x less than infinity. Correlation of successive samples which are generated through bit Thusworthy generator is r is equals to minus root or minus 2 in of u0. F of x is equals to lambda into v power minus lambda e power lambda into x if x greater than or equal to 0. 0 otherwise if x less than 0. Up to this point, pseudo-random samples are generated by only considering the probability distribution. In addition, there are other methods that focus on generating samples with specified probability distributions and power spectral density. In this, a method is proposed to generate realization from a wide sense stationary random process with a given continuous power spectral density and with a given first order marginal PDF. This method is based on addition of cosine signal whose amplitude, phase, frequency parameters are random variables. The method uses the following equations are x of n is equals to 1 by under root m square m by 2 summation of I is equals to 1 to m ai into cos of 2 pi fi into n plus psi. PRN generator. The PRN generator is designed by improving our previous work based on the Box-Muller algorithm and capable of generating uniform normal Rayleigh and exponential differentials distributions. The main block diagram of the design is given in the figure. Uniformly distributed samples are generated by two 32 bits Tausworthy RNG block. Each block uses the Tausworthy noise generation method, which provides better randomness with lower resource utilization. The Python code for 32-bit generator is given. The use of two Taus RNG blocks is necessary for modeling normally distributed samples with Box-Muller method. Uniform samples with 48 bits can model the normally distributed samples with 8.15 seconds. In the ideal case, this value must be 1. The distribution quality of the generated samples depends on the value and increased with it. And it is normally distributed within the many samples and it can be used between the distributed samples within 8.15 seconds. And here is a CPRN generator where the amplitude generator and phase generator is connected to sine and cosine block and the frequency generator is connected to the IFFT. And each which provides some randomness with lower resources utilization, and these capability of generating uniformly and uniform normal railings and exponential, and in y-axis they use some distribution such as uniform normal railing exponential, and they produce some graphs according to their distributions. Result. In order to show the effectiveness of the design, first PRN generator is used and digital noise samples are generated with different distributions by adjusting PRN parameters such as mean and variance and controlling switching multiplexer. Through PCI's based controller register, generated samples are fed into both 12-bit DAC and DMA interface, and they include some uniform sample and railings and exponential distributions. Adjusting some PNR parameters such as mean and variance are controlled with multiplexers. Here is a graph which is uniform noise samples. On x-axis we can see the number of samples and y-axis which are normalized magnitude. They include some railing, exponential, normal and uniform sample distributions. Conclusion. This article presents the design of real-time pseudo-random number generators for different probability distributions, also normally distributed samples with uniform power spectrum distributions have been generated. These design can be used for testing noise radar detection performance for different noise distributions, and for different noise distributions it can produce some different noise radars, and we need to test the noise radars according to the performances so that we can detect some real-time pseudo-random number generators according to the probability distribution. Here we can see the graph which produce a different noise productions and the frequency generations. So, according to the different noise distributions, we need to test the noise straders so that we can perform some different noise distributions, and it can design some different probability distributions. Thank you.